Hello, I am Sam Smith, and this is Sam's MCAT Basics. This podcast covers the most important topics put out on the AAMC MCAT each year, and I determined this list by going through all the official practice materials that the AAMC puts out, and also some third-party practice material, and just put together this big list of topics that consistently kept on showing up, and ranked those topics and made podcasts out of it. This lecture is going to cover light and optics. So as I'm sure you know, light has both particle and wave-like behavior. Therefore, it's only natural I talk about photons, which are particles, and then also about waves. So this podcast is going to be broken down into three main core topics. I'm going to start out discussing photons, mainly regarding their energy. I'll talk a little bit about the photoelectric effect. Then I'll get onto waves. I'll talk about simple harmonic motion. I'll talk about longitudinal versus transverse waves, and also discuss interference a little bit. And then I'll tie together photons and waves, and I'll talk about light. And so this will be a heavy physics lecture. I'll talk about polarization, reflection, refraction, and then lenses and ray tracing. And so as I said, this information will mainly come up on the chem physics section of the MCAT. That's 1 out of 4. However, in terms of physics, this is probably the most high yield. They like to talk about this in terms of eyeball and, your eye does this, or the way the MCAT likes to phrase questions is in terms of physiology. It's easy then to ask questions about optics because that is very related to the eye. So that's all I really got to say. Just get ready for a pretty information-dense, equation-dense podcast. All right, so light is a form of electromagnetic energy. And so like all other forms of electromagnetic energy, it has both wave-like properties and particle-like properties. And I already have, or I'm working on a podcast that's about atomic chemistry. And I'll put this out probably the week after I put this podcast out. But you can go back and hopefully, maybe if you're listening to this right now, this will already be out. But I talk a lot about quantum mechanics, and I think it has a little bit of a better background in terms of some of the things I'm going to talk about. But what this means for physics is that you'll see calculations involving both waves and photons. And so the first thing I'm going to talk about are photons. So photons are a particle that carries force for electromagnetic waves. In other words, they are small, massless particles that carry energy and light, which again is a type of visual electromagnetic wave. Most of the calculations you'll see involving photons are in terms of energy. So the energy of a photon is equal to hf, or hv, where h is Planck's constant, which is 6.6 times 10 to the minus 34, and f or v is equal to frequency. And so one thing you need to understand here is that you can convert between frequency and wavelength using the speed of light. So this equation is c equals v lambda, where lambda is equal to wavelength, and again, v is equal to frequency. So in this case, all you got to do is remember that the speed of light, which is 3 times 10 to the 8th meters per second, is equal to the frequency times the wavelength. And that way you can interchangeably do calculations between both frequency, or I guess using both frequency and wavelength. So for instance, you may be asked something like, in Washington, D.C., the police department uses a scanner frequency of 700 megahertz. What energy are these photons being transmitted to the police scanners? Okay, well, first you got to understand what is a megahertz. Well, first of all, a hertz is the standard measure of frequency, and it is 1 over seconds. Mega is the prefix, and it is 10 to the 6th hertz. 1 times 10 to the 6th hertz. So this would be 700 times 10 to the 6th hertz. Again, very important that you know these unit conversions, especially for the metric system. And so all you got to do here is think, all right, I have the frequency, I have the Boltzmann's constant, or most likely they would give that to you. So let's say you have those two and you need to know the energy, okay, of a single photon. Easy. You just pull out the equation E is equal to hv. do your multiplication through, and you would come to find out that this is about 4.5 times 10 to the negative 26 joules. So that's again for a single photon. This is just very low energy, which makes sense, right? Single photon, that's teeny, that's nothing. All right, cool. So calculating energy of a photon, very easy. What about this phenomenon known as the photoelectric effect? What is that? So the photoelectric effect occurs when a metal is blasted with a beam of photons. And what happens is this metal that is getting blasted with the photons will actually start to emit electrons. The important things to understand here are why this happens and what exactly is this work function that goes along with the photoelectric effect. So I want to start this discussion by talking about some observations that scientists made when they were first investigating the photoelectric effect. So the first thing they noticed is that the kinetic energy of these electrons that were ejected increased with light frequency. Okay, that makes sense, right? As you increase light frequency, you're increasing the energy of the photons. So it seems like when you put more energy in, right, you're getting more energy out. You're making these particles that eject out go faster because you're inputting in more energy. Okay, makes sense. The next thing that they noticed is that the kinetic energy of these photoelectrons being emitted remained constant as light amplitude increased. So what is light amplitude? Light amplitude is actually the number of photons that are being blasted at that surface. So that's just the number. And so that's kind of interesting, and I'll talk about why that is here in a bit. And these observations went against the common understanding of light at that time. Scientists thought that it essentially only acted as a wave. But if it only acted as a wave, then these observations, they didn't quite explain that. And so what happened was this experiment, or the photoelectric effect, actually helped physicists to establish the wave-particle duality of light. And so let's go back and let's talk about what is happening when you shoot a stream of photons at a metal. So two different things can happen. Either you shoot this beam of photons at the metal and you start to emit electrons from that metal, or you blast this metal with a beam of photons and no electrons are emitted. What's the difference? Well, depending on which metal that you're blasting, these electrons will actually have a minimum frequency that they need in order for their emission to occur. In other words, if these photons are not at a high enough energy, then these electrons will actually not be able to be emitted. So this gets at the work function. So let's say that you are blasting a metal with photons, and these photons are actually emitting electrons, or causing the metal to emit electrons. So let's take a deeper look at this. So the energy of the photon then is transferred to the kinetic energy of the electron and the work function. In other words, some of that energy that the photon contained goes to actually activating that electron to then be emitted. So this is basically, the work function is then that minimum bit of energy you need in order to dislodge that electron that then can be emitted. So once you get more energy than the work function, that energy goes into speeding up the electron or increasing that kinetic energy. So again, to recap, the energy of a photon, when we have this emission occur, it gets transferred to both the kinetic energy of the electron, which corresponds to speed of the electron, and it also transfers to the work function. So the work function is essentially the amount of energy you need to dislodge that electron, kind of the activation energy, if you will, in order to get that electron to be emitted. All right, so I'm going to give you a quick real-life analogy. So let's talk about work function in terms of fighting. So think about, what would your work function be in order for you to actually get in a physical altercation or a fight? Is there some initial amount of pissed off or some kind of threshold that needs to be broken for you to fight? This could be as simple as someone actually physically putting their hand on you. This could be somebody, talking shit to your girlfriend, boyfriend, whatever it is. There's something that's going to set you off. And so that's kind of that's your work function, right? There's this initial amount that you need to get over before you're boom into fighting. So, and obviously this changes person to person just like it changes metal to metal. But just understand that in terms of fighting, if you were to think about it like a work function, it would be that initial whatever has to happen for you to fight, right? For instance, for myself, my fighting work function is if someone starts to talk trash about the Broncos, right? Those are fighting words. That gets me over that little hump of energy. I'm out. I'm ready to be ejected. Okay, so the next place that you might see photons on the MCAT is in the emission absorption spectra. The absorption emission spectra of hydrogen is the most important to understand, and you can apply this basic general concept to all the other emission absorption spectra. So just know that atoms can either absorb or emit photons, and when an atom emits a photon, an electron moves to a lower energy level. On the other hand, when an atom absorbs a photon, an electron moves to a higher energy level. And this makes sense, right? When you're emitting a photon, you're emitting energy, therefore you need to balance that energy since energy is neither created nor destroyed. So when you emit that energy, you need to have a drop in energy in the atom, i.e. that corresponds to an electron moving from a higher to a lower energy. Same goes for absorption. And based on what we know from quantum mechanics, we know that these electrons can only be at very distinct energy levels, right? This is not a continuous spectrum. They're very distinct points. And essentially what these electrons do is they hop between these energy levels like Frogger, right? Frogger can't continuously go across the street. He hops between the different rows of cars. So you can kind of think of it like that. And so it's important to know then that this energy that's released, let's say when an electron goes from a higher energy state to a lower energy state, this photon that's released has some energy. And what is that energy? Well, the energy that this photon has is the difference between the starting point of that electron and the end point of that electron in terms of energy. And so you can say that is the energy of state 2 minus the energy of state 1. And again, that energy goes to a photon, and so that is equal to h times v, or Planck's constant times frequency. In other words, if you are able to measure the frequency of some light or of some photon emitted from an atom, then you can calculate the corresponding energy change of some electron that has now gone to a lower energy level. And so, I could see a question on the MCAT saying something like, you have an atom and it emits a photon with a known frequency. Here's the frequency. Now, then maybe they show a graph of the different energy levels of a hydrogen atom, for instance, of the electrons of a hydrogen atom. And now they say, okay, you know that this electron started at the third excited state, and you emit this photon. Now, what energy level are you ending up at, right? Because you could drop down from the third excited state to the second, or from the third to the first, or from the third all the way down to ground state. But it all depends on the frequency with you emit that photon, right? If you emit a photon with a very high frequency, then you have a very high drop in energy levels, right? Maybe you're going from 3 all the way down to 0 or ground state. And so going back to the hydrogen atom, there are 3 different emission absorption series to know. And so all a series are a sequence of lines that correspond to atomic transitions, each ending or beginning with the same atomic state in hydrogen. And so what do I mean by same atomic state? That's just saying that, all these series either start at the third excited state, or they end at the third excited state, or they start at the second excited state, or end at second excited state. So that would be 2 different series. So the 3 series that you need to know are called the Lyman, the Balmer, and the Paschen series. And hopefully this rings a bell from general chemistry, but if not, let's talk about them. So the Lyman series are emission absorption that start or end at hydrogen's ground state, which is n equal to 1. Remember what n is, that's the principal quantum number. So these are electrons that are starting at the ground state. And that's, for instance, let's say that an electron moves from the ground state, which again is 1, and moves to the second excited state, which is n equal to 3. So it just went from 1 to 3. Now what happens is during this move, you have to absorb energy, right, to move from a lower state to a higher energy state. So what happened, in this case, you absorbed a photon. The next series you're going to want to know is called the Balmer series. And these are emissions or absorptions starting or ending at hydrogen's first excited state, which is n equals 2. So that's something like an electron moving from the n equals 4, which is the third excited state, down to n equals 2, which is the first excited state. So what would have to happen in this case? You would have to emit a photon, right? You're going down in energy. So a photon would be emitted, and the frequency of that photon would correspond to the energy difference between the first and the fourth excited state. Lastly is the Paschen series, and these are emissions or absorptions starting or ending at hydrogen's second excited state, which is n equals 3. So an example of this would be, an electron starting at the third excited state, n equals 2, and then moving to the sixth excited state. And so then, again, you'd have to absorb some kind of photon in order to get to that higher energy level. And at this point, I was going to make an excited state joke, but that's low-hanging fruit, and my jokes are better than that. And if you have no idea what the principal quantum number is, I am putting out the next podcast, and that is going to be on atomic chemistry. I'll have a whole part where I cover quantum mechanics and quantum numbers and stuff, so hopefully that will illuminate this for you. So to briefly recap what I just said, there are 3 different absorption emission series to know, and what's important to understand there is that these different series either start or end at the same energy level. It's also important to understand that the emission or absorption of a photon corresponds to a change in energy state of an electron, and that change in energy state of the electron is proportional to the frequency or energy with which the photon is either emitted or absorbed. And in terms of quantum numbers, the wavelength or frequency of this photon is actually proportional to the difference in the inverse squares of the principal quantum numbers. And, that might be a bit abstract. If you want to go learn more about that, go look up the Rydberg equation, and that'll give you more of a visual way to kind of see how that works. But, I think just have a understanding of these concepts, and if there's a question that involves the Rydberg equation, I'm assuming that the MCAT would actually give you that equation, so I don't think there's any need to memorize that. Just understand the underlying concepts behind it. All right, so that was a brief introduction into photons and energy of light. The next thing I'm going to talk about are waves. As I said previously, light has both particle-like behavior and wave-like behavior. So I talked about photons, that is the particle-like characteristics. I'm going to talk now about waves. So there's 2 different types of waves you have to know for the MCAT. The first are longitudinal waves, and the second are transverse waves. Longitudinal waves oscillate in the same direction as displacement. So these are things like sound waves. And you can kind of imagine that is like the way a caterpillar moves, right? So when a caterpillar moves, different segments of its body contract, other segments expand, and that expansion contraction is in the same direction that it moves. On the other hand, you have transverse waves, and in transverse waves, the oscillation is in the opposite direction of displacement. And these are viewed a lot of times as sinusoidal waves. So you can imagine, I'm sure you've seen a sinusoidal wave or even like a tidal wave, right? So they're moving towards the shore, but these waves are going up and down. If you put a bobber in the ocean, you'll notice it keeps bobbing up and down, but the waves are moving in the opposite direction, or in a perpendicular direction to that bobbing motion. And again, that is a transverse wave. And there are a few features of waves I want to talk about. The first is the wavelength, and this is the length of one complete wave cycle. Then there's amplitude, and the amplitude of a wave is the maximum amount of displacement of a particle on the medium from its rest position. And if you're looking at the graph of a sinusoidal wave, which you're likely to see on the MCAT, this would be the maximum distance up from the x-axis where the wave reaches. And so the next term I want to talk about is troughs. And so a trough on a wave is the point on the medium that exhibits the maximum amount of negative or downward displacement. This is a peak that is in the negative direction. Then you have crests, which are the same thing as troughs, just in the positive direction. This corresponds to the amplitude, right? This is the highest point on the medium that the wave reaches. And then the last thing I want to talk about is period and frequency. So the period of a wave is the time it takes to complete one cycle. Pretty easy to remember. And then frequency is very related to period. It's the inverse, and so this is the number of wave cycles that are completed in 1 second. So pretty easy to convert between frequency and period. Period is just 1 over frequency, and frequency is 1 over period. It's also important to understand what happens when waves collide. And this is easiest to think about, I think, in terms of ocean waves. So what happens when two waves are produced and travel towards each other, and the one trough hits the crest of one wave, and what happens when two crests meet, or what happens when two troughs meet? And so you can think about this in terms of the principle of superposition. And this states that waves pass through each other without being disturbed, and the net displacement of the medium at any point in space or time is simply the sum of the individual wave displacements. In other words, the waves simply add up, right? If you have the trough of one peak and the trough of another peak, those add up to make an even bigger trough. Or same goes with crest. But what happens when you have a crest meet a trough? Well, then you get cancellation. They're going to cancel each other out. And obviously, if one crest is a lot bigger than the trough, then you're just going to have a subtraction in size of that crest. But if they're both the same sizes, they'll cancel each other out perfectly, and you will get zero displacement. And so these phenomena are called constructive interference and destructive interference. Constructive interference is the case I was talking about, where either the crests or the troughs of two waves align, and these amplitudes add together. And essentially what happens is you get two waves that come together to create an even bigger wave. Destructive interference is the second example I mentioned, and that is when the crest and the trough of two different waves align and they cancel each other out. And interestingly enough, destructive interference is the principle by which noise-canceling headphones work. So if you've ever put on noise-canceling headphones, you know that you have to turn them on with a little switch. And you know, why is that? Why can't you just put them on and they work? Well, what's going on is that you are actually turning on a microphone. And so what happens is these headphones listen to the sound coming in, and they send out waves that are the exact opposite of the waves coming in, and through destructive interference, they actually cancel out those sound waves. And that is why you don't hear anything, because those sound waves are actually being canceled out as they come and try to enter the headphones through the ear. So that's a brief discussion on waves. Just understand here kind of what the different aspects of a wave are. You know, what is a trough? What is the amplitude? What's the wavelength? I think that's the most important thing to understand here. What's more important, though, is how to apply these in terms of physics. And that's what I'm going to talk about next. I'm going to talk about lenses. I'll talk about what happens when light enters different materials. That includes refraction, reflection, etc. And then lastly, I'll talk a little bit about polarization. All right, so the first thing I want to talk about here is polarization. And so light can be polarized when it is passed through a special filter. And so, you might have a pair of Ray-Bans that say polarized, and you don't really know why that's better, or is it better, but it sounds pretty cool. And so what a polarizing filter does is it actually selects a certain angle of light. And so I'll get into what that means. Imagine you have a piece of paper and you drew a two-dimensional light wave on there, right? Just a sinusoidal wave. Now you take that piece of paper and you rotate it 365 degrees, right? There's 365 degrees in a circle. Just kidding, that's days in a year. There's 360 degrees in a circle. So imagine rotating this now 360 degrees. And so any light that's not polarized can be at any of those angles as you rotate that piece of paper. However, what a polarizing filter does is it acts almost like a fence. Imagine a fence with slits, right? And now you're trying to pass that piece of paper through this fence. Well, if that piece of paper is perpendicular to the fence slits, it's not going to go through. So in this same principle applies to polarized light. These filters essentially select for a certain rotation of this light. And then the light that goes through that filter is all one angle. Another analogy is throwing a Frisbee through a fence slit, right? So you have to throw it kind of overhand, like a tomahawk throw. If you throw a Frisbee just like you normally throw it and try to make it through a fence slit, it's not going to work. So again, this kind of gets to the point that a polarizer polarizes light to a certain angle. And so there's a few different ways you can polarize light. Obviously, you can polarize through a filter. Refraction polarizes light, and reflection also polarizes light. Another very important example of a light polarizer is chiral molecules. So it's important to understand that chiral molecules can actually polarize light. They'll all select for a certain angle of light. And so that's important to understand because you might be reading a passage and it's going to say something like scientist X has created this new cancer drug, and they expose this cancer drug to unpolarized light and find out that the light leaving is actually polarized. Well, now you know that molecule is chiral. All right, so other than understanding the general concept of what happens to light as it passes through a polarization filter, it's also important to understand what happens to the intensity of light after it becomes polarized. So as I said before, unpolarized light kind of radiates in all these different directions, in any degree out of 360, doesn't matter what its rotation is. So what happens when you pass this through a polarizer? So it polarizes to a single degree, but what's important to understand here is that its intensity is actually cut in half. So unpolarized light that's passed through a polarizer, its intensity decreases by a half. And you can go through the math and kind of figure that all out if you want, or you can just remember that if I have unpolarized light and I filter that through a polarizer, its intensity decreases by half. Pretty easy to remember. What about the case where you have already polarized light and you pass that through another polarizing filter? Well, this follows what's called Malus's Law. And so this is that the intensity of this second filtered light is equal to the original intensity times cosine squared theta. In other words, if this light entering the second filter is perpendicular to the filter itself, none of that light will pass through. And as you rotate that light closer and closer to the angle of the filter, you will get more and more of that light through. And that makes sense, right? You have a filter that's essentially a slit, and as your light becomes more and more parallel to that slit, more of that passes through. Again, like the Frisbee and fence example. So to briefly recap everything I just talked about. So when you pass light through a polarizer, you select for a certain plane or a certain angle of light, and the intensity of unpolarized light that becomes polarized is half the initial intensity of light. And then let's say you take that polarized light and you pass it through another polarizer, you decrease the intensity, and this depends on cosine squared theta. And again, if that second polarizer is perpendicular to the angle or plane of light that is coming in at it, then nothing is going to pass through, and the intensity is 0 because no light gets through. And so just a quick anecdote about polarization and sunglasses. So, when I was a kid, I'd go fishing with my dad, and he'd always make sure that I had polarized sunglasses. And at the time I was too young to really understand why this is or why I needed polarized sunglasses. But essentially what's going on is light that bounces off the water where you're fishing in, which is, again, reflection, becomes polarized. And so when you have polarized sunglasses, you can actually filter out a lot of the polarized light because you're selecting for a certain angle of light. And so that reduces glare because you cut out a lot of this polarized light that's bouncing up and into the sunglasses. And therefore you can see fish better, you can catch fish better, and you can eat fish better. All right, so what happens now when light passes through opaque material? So what happens is light can either be reflected or it can be refracted, or both. And so what happens is when it enters these different materials, it will either slow down or it will speed up. And so when light enters more dense material, it tends to slow down. And when light enters less dense material, it typically speeds up. And so, the example here is air versus water, right? What's more dense? Well, water is like 1,000 times more dense than air. So when light goes from air to water, it actually slows down. And it's important to note here that the frequency of the light doesn't change through different mediums. Don't forget that. And again, the speed of light is equal to lambda times v, or wavelength times frequency. So if frequency isn't changing and the speed of light is going down, then what is changing? And that's wavelength. So again, important to understand that the frequency of light doesn't change through different mediums, only the wavelength changes and the speed. And so on the MCAT, you will be given different materials and different refractive indexes for these materials. And so, for instance, water has a refractive index of 1.33. Air has a refractive index of 1 approximately. Under vacuum, it's exactly 1. And so this corresponds to the density and also the speed at which light travels through this medium. More importantly, the refractive index is the speed of light through a vacuum, which is 3 times 10 to the 8th meters per second, over the speed of light in the medium. So as n increases, that corresponds to light slowing down to a greater extent. So something with a very high refractive index like diamond, which is 2.44, will actually slow down light a lot more than something like water, which has a refractive index of 1.33. All right, so that's all good and dandy. Light slows down as it enters more dense materials, which have greater ends or greater refractive index. But what happens to the actual light as it enters this material? Well, light follows what's known as Snell's law. And Snell's law is n1 sine theta 1 is equal to n2 sine theta 2. And so what Snell's law says is that n1, or the refractive index of medium 1 times sine of theta 1, we'll call that the angle of incidence. So this is the angle between the ray of light and the normal line, which the normal line, again, is the perpendicular line to the surface of the medium. And that is equal to n2, or the refractive index of what the light is entering, times sine theta 2, which is the angle of refraction, which is the angle between the normal and the ray of light that has been refracted. And so what does this mean for different materials? Well, if you have a ray of light and you're beaming that in to water from air, then you're going from an N of 1 to an N of 1.33. So you're going from a less dense material into a denser material. Then your ray of light actually bends towards the normal line. On the other hand, if you were to shine a light out of a pool, let's say, so now you're going through water into air, then what's happening? Well, the light in that case is actually speeding up as it enters air, and you're going from a medium with a higher N or a higher refractive index into a lower refractive index. And so what happens in that case is, number one, the light speeds up, and number two, the light bends away from the normal line. So let me briefly recap that. So when you're shining a light into a material from a lower refractive index into a higher refractive index, the light slows down and it bends towards the normal line. On the other hand, if you are going from a material that has a greater N or is more dense, and you shine a light through that into a material that has a lower N or is less dense, light is going to speed up and it is going to bend away from the normal. And if you need to calculate exact angles, use Snell's law. Another thing you might see in the MCAT is total internal reflection. And so essentially what occurs in total internal reflection is that the light is actually reflected back into the medium that it came from. Instead of being refracted into the second medium that it's entering, it's reflected back into the medium where it came from. And why does this occur? So this occurs when the angle of refraction is greater than 90 degrees. And it's important to understand that this can only occur when you're going from a medium that is more dense into a medium that is less dense. In other words, you have a material with a high N or a high refractive index, and you're going into a material with a lower refractive index. It's the only way this can occur. And so one of the values that's related to total internal reflection is the critical angle. So the critical angle refers to the incident angle in which you get a refractive angle equal to 90 degrees. And so all you do to solve for this is you input 90 degrees into Snell's law for the refractive angle, and this simplifies to 1. You input in your N1 and your N2, and then you solve for that incident angle, and that is the critical angle. And so the last thing I want to talk about here are lenses and ray tracing. So there's two different types of lenses. There's converging lenses and there are diverging lenses. Divergent lenses are thin in the middle and then thicken out as you get to the top and the bottom of the lens. If you don't know what I'm talking about, just go Google divergent lens and you'll see what I mean. And this is also called a concave lens. And what it does to light is when you pass light through it, it actually makes all the rays diverge away from each other, which makes sense. It's a diverging lens. You also have converging lenses, and you can think about these as the thicker kind of lens, very thick. And so they're round in shape, very nice to look at. And what they do is they cause rays to actually converge to a single spot. And that's obviously in contrast to a diverging lens. And these are also called convex lenses. All right, so now that I've introduced convergent and divergent lenses, let's talk about the most important equation to understand in terms of lenses. And that is the thin lens equation. And before I introduce this equation, I want to discuss what exactly is a thin lens. Well, a thin lens is essentially a lens in which the thickness of the lens is negligible in terms of calculations. This means that when the light hits it, it only refracts once because the lens is so thin. And if this is not the case, then you have what is called a thick with two C's lens. In terms of the MCAT, all I've ever seen are thin lens problems, so I wouldn't even worry about thick lens. And that's why I'm only going to talk about the thin lens equation here. So the thin lens equation is 1 over the focal length is equal to 1 over the distance from the lens to the object plus 1 over the distance from the lens to the image. And so it's pretty self-explanatory in itself, the equation. When this equation gets hard is when you're trying to determine, is this image real? Is it virtual? Is this image on the left or on the right side of the lens? And then also you can determine magnification using these variables. So let me briefly touch on what real and virtual images actually mean physically. So when you pass light through some kind of a lens, that light is going to converge and create an image. And so a real image implies that the image of that object arise at an actual real point. Whereas a virtual image, these light rays appear to converge at this point, but are actually divergent light rays. And yes, this is a bit convoluted and hard to understand, but just know that for a virtual image, the rays are not actually converging to where this image actually appears. What's 100% more important to understand is what these different images mean for the sign of the image. And so for a real image, the sign is going to be positive. So in other words, the distance from the lens to the image is positive. And for a virtual image, you will have a negative distance from the lens to the image. And this says that the image is actually on the same side of the lens as the object when it is virtual. So let me reiterate. Real image, distance from the lens to the image, positive. For a virtual image, the distance from the lens to the image is negative. Now, another important sign convention in terms of this equation is the sign of the focal length. So for convergent lenses, the focal length is positive, and for divergent lenses, the focal length is negative. So now that you understand these two sign conventions, you really should be able to solve any problems, right? It's essentially plug and chug. You just need to be able to understand that, say they give you a focal length and they say this is this divergent lens that you're using. Well, now you know, okay, this focal length needs to be negative in the thin lens equation. They'll give you the other numbers, you plug in, you solve for whatever you don't have. It's pretty easy. And these problems are not too bad once you understand the sign conventions. And so lastly, you may be asked to use the magnification equation. And so that just says that magnification is equal to the height of the image over the height of the object, which is equal to the negative distance from the lens to the image over the distance from the lens to the object. So those are two kind of different ways to calculate magnification, either using the height of the image, height of the object, or using, more likely, you'll use this form, which uses the distance to the image and distance to the object. And in terms of sign convention, this is pretty interesting. So when the magnification is negative, that means the image is actually inverted. When it's positive, it's upright, and you will have a magnification when this number is greater than 1. So greater than 1, you have a magnification. Less than 1, then you are zooming out, or that the image is smaller than the object. In other words, it's been minimized. All right, the last equation here is the power of a lens. And the power is just equal to 1 over the focal length. And so convergent lenses will have positive optical power, while divergent lenses will have negative optical power. And essentially, the power of a lens corresponds to how powerful the lens is at actually bending light. And this makes sense, right? The smaller the focal length, the smaller the focal point, which means the light will converge at a closer point, and therefore the lens is more powerful at bending that light or at converging that light. All right, the very last tool that you need to have in terms of solving these lens problems is being able to do ray tracing. So if you go back to your sophomore year physics or whenever you took physics 2, this was kind of pretty heavily focused on, or at least in my class it was. And so this will help you kind of see that you got the right answer. This will help you check your work. I don't know that you'll necessarily see a problem directly related to this on the MCAT, but this will definitely help you check your work for problems in which you use the thin lens equation. And so when you do ray tracing, you draw 3 principal rays. The first is a ray that goes into the lens parallel and then goes out through the focus. The next is a ray that goes in through the focus and out parallel. Then the last ray is a ray that goes just straight through the focus. And what this will do is this will show you where the image lies. And that'll tell you, number 1, is this image inverted? It'll tell you how big is this image? And then it will tell you if the image is virtual or real, right? If the image is real, this image will be on the opposite side of the lens as the object. And if this image is virtual, it'll be on the same side as the object. And so for physics like this especially, you really need to practice these topics, work through actual questions. Put pen to paper, really make sure you know this stuff. So yeah, that's my recommendation. That's my MCAT advice of the day, is to really just go nail down physics through lots of practice problems, draw everything out, and especially when you're taking the MCAT and you have this sheet of paper in front of you that you can draw stuff out on, and it's like a whiteboard marker and a whiteboard like a sheet of paper, but you have this in front of you that you can use to help you solve problems. So of course you should draw out the ray tracing and do the whole diagram on a problem, right? And that just is going to increase your rate or your chances of getting that problem right. So my advice is to go practice these topics that I just discussed. Make sure you know how to draw rays, how this refraction works, and be able to use these equations. All right, and so that concludes the episode on light and optics. As always, thank you for listening. If you liked it, go rate it, or give me feedback if something doesn't make sense or something's not right. Let me know. Shoot me an email. Thank you for listening, and I hope this helps.
Hey, what are you doing? Hey.
Sam's MCAT Basics is written, produced, and recorded by Murph the Dog. Special thanks to Murph the Dog for this episode.